Okay, welcome to the second and last session of today. So I'm happy to introduce as our first speaker of the session, Eva Löcherbach from the University of Paris, Panthéon-Sorbonne, and she will talk about mean field limits of spatially structured Hawkes processes.
Yeah, thank you. Thank you for the invitation. I saw that you have beautiful blackboards in the room, so I would have loved to be there and to give a real blackboard talk, but it has not been possible, so I will show my slides. So this is a work we did some time ago together with Julien Chevallier. He's in Grenoble, Erny, Duarte and Guilherme, two Brazilian guys. And it's on mean field limits of spatially structured Hawkes processes. And actually, the main motivation we had in mind was to model neurons and their sequence of spike trains. So during this talk, I will speak of neurons, but if you want to think of limit order books as in the previous talk, I mean, there are also some applications of Hawkes processes to order book modelings, if you prefer these kinds of applications. So I have a system of n interacting neurons represented by their counting processes. And so for each neuron, I attach it to a position in space, say in RD, and attached to that position, I have a counting process counting the number of spikes, or if you want, of transactions of a given asset, so during 0t. So Zi n of t is a counting process, and it has a jump rate which is stochastic and which will be called lambda I n of t throughout the talk. And this is a deterministic function f that I will call spiking rate of a given quantity which we interpret as the membrane potential of the neuron I at time t. And this potential follows this red equation here. So we have some exponential loss at rate alpha of the initial potential, which is this u naught of xi. So remember, xi is the spatial position to which is attached the neuron. And then we have interactions. That means that I sum over all other particles j. I see what are their jump times in the past. So at any time s in between 0 up to the present time t. And if the particle j jumps at that time, it will give an additional kick, which is this little w here that I call the synaptic rate. And that depends actually on the positions of the giving particle, so xj, and the receiving one, which is xi. And it's renormalized by the system size. So the jumps are actually small jumps of order 1 over n, okay? And then we still have the exponential loss of all these influences over time. So this is the usual convolution kind of definition of the intensity of a Hawkes process. If you know these processes, but it's nonlinear because we put all these interactions into this nonlinearity, this deterministic function f, okay? So just to be clear what I'm speaking about, all these processes, so the different particles, neurons or assets are driven by independent Poisson random measures. These pi I here, so they are independent, they all have Lebesgue intensity in time, which is the little s, and space z. The z is just an acceptance rejection variable that we use in order to accept or reject the proposal jumps by the Poisson random measure according to the present state of the jump rate lambda I n of s. Okay. So this is the model. I just recall here the definition of the intensity at time t, because this is actually the main ingredient, of course. So we have, say, 3 parameters. There is this firing rate function f, so which is a function defined on R, taking values in R plus. Then we have this, I call that the matrix, but it's actually, well, it's a function, the little w is a function on positions times positions, so of the giving and the receiving particle. So depending on the position, and we call that the matrix of synaptic rates. And just to recall, so we read the interactions from left to right. Okay, so the giving particle, so the one which is jumping is the left one, and the one which receives is the one in position x, right? And then we have the leakage weight, so the weight at which we lose memory, which is this parameter alpha. And of course, the initial input to all these potential values, which is the function u0. So this is, I already said that, a multivariate Hawkesprocess because it's n interacting point processes. It's nonlinear because of the function f. And if you want to read a wonderful paper that that is basically the state of the art of the stability theory of these kind of point processes, there's the paper by Pierre Brémaud and Laurent Massonnier from 1996, which is really a good paper and which gives you a good review of all this. So of course, in the sequel, I said I will speak of mean field limits. So I will let n tend to infinity. And the question is, where does this process tend to, and in which sense? And of course, for this, we need some conditions on all the parameters. But before doing so, let me just stress that since we have this exponential decay, the process is actually a Markov process. So if we look at the process of membrane potentials for all the particles at time e, so these u, I, n of t, which are these ones here in the red formula, well, this is actually a piecewise deterministic Markov process in dimension n, and its generator is given by this formula. So for each u, which is a collection of potentials, we have the exponential loss of each of the potentials at weight alpha. Alpha is the same for every particle. And then there is the jump term, which is the second term here. So we have the sum I equal 1 up to n, f of ui. So this is the jumping weight of the ith particle. So it depends on its actual potential value. The jumping weights, it's a sum, which means that the underlying Poisson processes are independent. And if it's I that is jumping, then each particle j will receive an additional potential value, which is this w of xi, xj divided by n, okay? The ej here means it's just the jth unit vector on Rn. Okay, so you see, we basically have a jump weight, a total jump weight, which is of order n, if we suppose that f is lower bounded, something like that. So the total jump weight is of order n, the jump height is of order 1 over n. So of course, there will be some limit process where basically this term here will be replaced by a drift term, okay, for the limit process. But before doing so, I have to say something about the values of the spatial positions. Will be 2 slides later. So I try to make a picture because I'm not in front of the blackboard. I'm not sure that's really very clear. So I have the positions somewhere in space. So this is x1, x2, x3 up to xn. And attached to the positions, you have to think that we have these processes that count the jumps. So here's the jump process of x1, the one of x2, of x3, of xn. And then we have interactions in between these nodes of the graph, if you want, which are given by the w's. And there is an interaction if and only if the associate w, for example, is different of 0. So the interaction from x2 to x1 is given by w of x2, x1, and so on. Okay, so this is the finite particle picture. So the conditions are the typical conditions that we need if we want to be able to pass to the limit. So we suppose that the firing rate is Lipschitz globally. The potential input initial, this u naught of x, which is a function of space, we need it to be bounded in space and Lipschitz in the space position. And then the matrix of synaptic weights, well, we suppose it's Lipschitz in both of its components, x and y, you will remember because I have these interactions in there. And then I need some boundedness condition on it. Basically, we need that the interactions are bounded in this sense here. So this is actually the condition we need in the sequel of the talk. So there will be some a priori probability measure rho, which will turn out to be the spatial distributions of the particles. And then I need the finiteness of the interactions in this uniform sense. So I integrate with respect to the giving particle according to rho, and I take the square of the interactions and an analogous condition in the other sense. Okay. This slide, there's no need to read it, but it's just to tell you that we have some uniform bounds on first and second moments of the counting processes at each step n, and these bounds do not really depend on n, except that they depend on these bounds on the interactions where I integrate the receiving particle against the empirical measure of positions, okay, which is this mu n. So this is the empirical measure of the spatial positions at step n, okay. So if you think that mu n will converge to this a priori measure rho, then you understand why I need this kind of condition here, because that's exactly the red parts here in the limit mode. Okay, so we have bounds on first and second moments of the counting processes. And that gives us some idea that we will have convergence to some limit counting processes which will have the same bounds. So in which sense do we have this convergence? So for that sake, we introduce the following empirical measure, which is actually an empirical measure on trajectories. So the eta here is the total trajectory over a fixed time interval 0 capital T of counting processes. And the second component is just the empirical measure of positions. Okay, so it's 1 over n, I sum over the particles, and then I put the Dirac mass in Zin of t, so in the total trajectory of the ith counting process, comma, and then little xi, because this is the counting process attached to position xi. So it's a random probability measure on the Skorokhod space, defined on some fixed time interval, and taking values in n, times Rd, the positions. And then an additional assumption, we suppose that the initial positions that we chose, x1 up to xn, are IID distributed according to some probability measure rho, and this is exactly the measure I was speaking about before. And for technical reasons, basically to be able to make a good truncations, we need this rho to possess some exponential moments. Okay, so these are our assumptions. And we will prove that as n tends to infinity, this empirical measure, so Pnn, so I take two n's here in order to show you that we have empirical measure in the trajectories, this is the first n, and empirical measure in the positions, and then the time interval is fixed. By the way, that also means that I don't need any ergodicity assumption actually to make this work. Okay. So we will prove that there exists a deterministic limit probability measure on Skorokhod space times positions, such that some Kantorovich-Rubinstein type of distance between the empirical measure and the limit measure converges to 0. And this almost surely with respect to any realization of these IID random positions x. Okay, so the distance we take is actually, well, this one. So we take the supremum over all Lipschitz 1 functions, and these are Lipschitz 1 functions of trajectories times positions. For the trajectories which are cut like, we just take the Skorokhod distance. And then we evaluate G according to the difference of the two respective measures, P and N minus its limit quantity. Okay, the expectation here that's important is only taken with respect to the randomness present in the jumps, so in the Poisson part, in the Poisson random measure part of my particles. So I work with respect to fixed realization of the random environment of the random positions. So first remark, according to our a priori bounds on the first and second moments, you immediately see that the limit measure, if it exists, does also need to satisfy the same moment bounds, which means that if I take the total number of jumps to the squared plus the total number of jumps, which is eta t to the squared plus eta t, and I integrate according to the limit measure, that is automatically finite. Okay, so this is by our a priori estimates. And a second remark is that, well, you see I have here the empirical measure in the trajectories times the jumps, times the positions, sorry, and the positions are IID. So if I project onto the second coordinate, of course, I will get in the limit the a priori measure rho as a limit of the second coordinate, okay, because they are just IID. So by the disintegration theorem, the limit measure automatically will take this form. So I have rho of dx, so I choose a typical position according to rho, and then given rho, I will have some law on the trajectories eta. And the question is, what does this conditional law of a counting process given x, so attached to a position x, look like? And this is actually not so astonishing. So I just recalled here the form of the intensity attached to the position xi that I imposed to the finite particle system. It's this one. And then we formally pass to the limit, which means that everything which is an empirical measure with respect to the position then becomes a theoretical empirical sum, sorry, becomes a theoretical integral with respect to the a priori measure rho, okay? So if I pass to the limit here, I will get attached to each point x, which is in the support of rho, this formula here. So the first term is the same, and this term here becomes an integral. And then, since I have here something like an empirical mean of counting processes, which are supposed to converge to some Poisson process, this will converge to just its intensity at position y ds rho dy. Okay? And actually, you will prove that given x, the law of the trajectory attached to that will be the law of an inhomogeneous Poisson process, which has intensity lambda of tx for fixed x, and the collection of all these lambda variables satisfies this convolution equation number 1. Okay. So this is the intuition. So for the moment, I didn't prove anything. So I just guessed the limit equation, and then the way of proving that we actually converge to this limit process. So a collection of Poisson processes which are attached to the positions, and conditionally on the position, we have the intensity lambda of tx, which solves this convolution equation. So the way of proving that is actually first proving that equation 1 has a unique solution. And once we have the solution, that actually means that we have the solutions for the expectations of the Poisson processes, and then we can just construct the limit process, which then exists in a unique way. Okay. So if we rewrite our a priori bound on the second moment and the first moment of the limit measure in terms of the intensities, so this bound here, this immediately gives you this bound on the integrals of the intensity over fixed time intervals. Okay, so we know that if the limit measure exists, if the lambda exists, then we have this kind of control. And then you just say, you prove easily that in the class of all solutions lambda of tx that solve these moment conditions, well, there is a unique solution of the convolution equation. And moreover, this unique solution is continuous in both variables, time and space. And it's uniformly Lipschitz continuous. That's important in the space variable, uniformly over time in compact time intervals. Okay, so that's easy to prove. And this actually, together with this following fixed point argument, shows that we have a unique solution for lambda. So this capital F of lambda is actually the equation that the limit lambda has to solve. So suppose I have a candidate value for the limit intensity, which is the lambda wet here, then the limit lambda must satisfy the fixed point equation that capital F of lambda is equal to lambda. So here I just replaced the definition of the limit intensity, okay? And then you just show that capital F as a function of lambda is a contraction if we restrict our attention to sufficiently small time intervals, which gives you both the existence and the uniqueness of a solution of the convolution equation for the limit intensity. Okay.
5 more minutes, please.
Yes, I have to hurry up. Okay. So here's the theorem. So since I convinced you that the limit process exists, so the distance, this Cantor-Rubinstein type distance between the finite empirical measure and the limit measure is given by the contribution of two values. The first one is a variance term, so n to the -1/2. And the second one depends on how far is the empirical measure of positions away from the limit measure in Wasserstein-2 distance. And then actually for this Wasserstein-2 distance, we have a control such that in the end we arrive at this rate of convergence, which depends on dimension. And this holds almost surely for all realizations of the particle positions. I give you a first corollary of that, which is something that the people call propagation of chaos, or if you want, multi-class population of chaos. So if we suppose that the spatial positions are Lebesgue continuous, then I take some kernel functions that localize the activity close to 2 points x and x tilde, which are in the support of rho. Okay, so phi n will converge to something like the Dirac mass in x, and phi n tilde to the Dirac mass in x tilde. And then I just want to evaluate the activity of the counting process eta close to x. Okay, and I call that Gn. So this is just a smooth version of the activity. Same thing for G tilde. And then our theorem tells us that the expectation of the activity close to x and the activity close to x tilde converges to this limit quantity where the expectation factorizes. Okay, so here we have the product of two expectations. And this is really the propagation of chaos, because this means that the activity close to x is independent of the activity close to x tilde. And if I take x different of x tilde, that means that in the two different classes, if you want x and x tilde, the activity is independent. And if I take x equal to x tilde, the result is still 2. And that means that within a class, we also have independence. I skip this, so there are some, we have some links with the neural field equations, which are equations on the potentials. I just want to give you a sketch of the proof. So the proof is in 2 steps. So I have the original empirical measure P and N, and then I proceed in 2 steps. So the P infinity N is just the measure where I keep the discrete distribution of particle positions, but to each position, I attach already the limit process, which is the Poisson process with the white weight, okay? And then here, this is the true limit process, so, okay. And then we should first show this is discretization in space and coupling in the Snitman way. So what does that mean? Coupling in the Snitman way means that to compare the first 2 of them, well, I have the same positions, and then given the same positions, I take the same Poisson random measures for the 2 processes to couple the finite particle process with the limit particle process, okay? And for this step, we have this control here. So we have a variance term, and then the Wasserstein-2 distance between rho and the empirical measure, and the total thing is multiplied by this by the maximal interaction term integrated against the empirical measure at stage n. The second step is to replace, compare these two ones. So this is again a kind of Snitman coupling. So we take any coupling of the initial positions, which are not the same because the measures are not the same. And then given the two initial positions, I take the same Poisson random measure to take to construct the corresponding limit Poisson processes. Okay, that just means that we force the two processes to jump together as often as possible. Well, and then you have also to control this interaction term here. Actually, well, there is this truncation argument. So actually, we show that at least if we stay within balls, then this interaction term is actually Lipschitz continuous with respect to its integrating measure here, up to some error terms, which comes from truncating the mass of the a priori measure outside some big ball. Okay. So this is why we need the exponential moments. And this is how we deal with the interaction terms. And then we use deviation inequalities for the Wasserstein-2 distance of the empiric measure of the positions and the limit a priori measure. And that's actually a nice paper by Fournier-Guillain in 2015 that I recommend to read. Okay. So I have to stop almost. I will just make two last remarks. So this is related, first of all, to multi-class systems of neurons, which I have studied together with Susanne Dietlefsen. So if you take rho, which is some discrete measure, that just means that we partition particles into some populations, little n populations, and then you can just impose interaction graphs on these on the level of populations. And we showed in this framework actually that in the limit process, there are oscillations that pop off. Okay. I skip this and I just close with this last remark. So in a recent paper together with other people, Dasha Loukianova and Xavier Erny, we studied actually the same model, but in a diffusive scaling. This means that, so I recall here the value of the intensity function. Instead of having 1 over n for the jumps, I will take 1 over square root of n, and then I will take jump heights which are centered to express that somehow in my system excitatory and inhibitory inputs are balanced. And apart from that, I did not really change the system, except that I put the jumping particle back to 0 each time it jumps, which makes sense from a neuroscience point of view. In this case, I have a limit process, say for the potential values attached to each position x, which is an equivalent way of formulating things, where we have an additional term which pops up here. So the capital M is a martingale measure, so it's something like a white noise, except that it has intensity dt in time rho of the x in space, that's natural. And then we have the conditional expectation of u given m, which represents actually a source of common noise in this limit system. And you see that the jump intensity f of y pops up as a square root term here. Okay. Good. And I stop here. And these are the references. Thank you for your attention. And sorry, I have been a little bit too slow.
Okay, let's thank the speaker. I'll first take questions in the audience here, and then if people online have questions, please use the raise your hand option. Yeah, one moment.
It's on. Thank you very much. I wanted to ask a question about the t in your proof of existence. You said that you get existence for small t.
Yes.
Is it only the case? Can you overcome it for any bounded t, or you have to have small t?
No, you concatenate actually. I mean, this contraction argument works over little t.
And then you put together, okay.
And then you put it together. You concatenate all these arguments. So.
Yeah. Alan Hawkes always worked in very close collaboration with a very strong group in neurosciences from UCL, and at least for the case of linear firing functions, they produced a huge lot of formulas for Barthes spectrum, correlations, etc.
Yes.
So how we could comment on this, or what you can contribute to this development from the point of view of applied science?
So you're speaking about one-dimensional Hawkes processes, I guess, in the sub.
They did Barthes spectrum for multidimensional system, but for some reason for linear, more or less, Fourier function.
Exactly. So this works very well in the linear case, because then you can write down everything explicitly. It works only if the process is subcritical. Here in the nonlinear case, it's you don't have any explicit work on this, I think. I mean, once you put the nonlinearity, because you want to include inhibition into your model, which is kind of natural, you lose all these very nice formulas that you have for the linear Hawkes processes.
What about small perturbations from linear case?
I didn't understand the question. I mean,
they consider small perturbations from linear case as well.
Yeah, I'm not sure if I'm aware of this work, but yeah, I have to look at it.
Okay. Okay, maybe just one very quick question here.
Just a small technical point. So there are two parts of your proof. One part you have this you compare empirical measure with the distribution of random variable, Fourier result, and another part is the coupling, right? So 1 over square root of n comes from the coupling. Is this coupling bound the best possible?
That's a good question. We did not prove that. I have the feeling that yes, but I did not think about it.
You said it comes from some variance estimate, or
exactly.
You
exactly.
you don't have lower bound for the variance then?
No.
That's the okay. Yeah. Thank you.
Okay, let's thank the speaker again.
Thank you.
And
I stopped sharing screen.